Alright gang, here we go. This is Physics Unit 6, Part 3. We're talking about fluid flow. Should be pretty easy stuff here. Alright. But it might help explain some concepts that you're totally used to using in everyday life. You just haven't quite thought about the physics involved with them. Okay. So in general, there are two types of fluid flow. Okay. Laminar flow or laminar flow. Okay, or turbulent flow. All right, laminar flow assumes that everything moves in smooth paths and that everything just goes just fine, perfect, that everything is in ideal conditions. Turbulent flow is when your fluid is going in totally random, irregular motions and it's hard to predict what's going on. All right. So, as you could probably guess, since this is kind of your first foray into fluid mechanics and fluid flows, is we are only going to assume that all of the fluids we're looking at are ideal fluids, meaning that they can't be compressed, there's no internal friction, there's no viscosity, and then they're non-turbulent. Okay, so essentially, I just want you to know that turbulent flows are a thing, but we're really only going to focus on laminar flows. All right, okay. So, fluid flows. Now, as fluid flows through a pipe that gets wider, okay, or the fluid flows through a pipe that gets wider as the fluid moves through it, okay, what would you expect to happen to the velocity? Now think about it in the reverse real quick. When you were a kid outside playing with the hose out in the yard, okay, you turn on the water comes out of the end of the hose, and then you cover the end of the hose partially with your finger, with your thumb. What happens to the velocity of the water as it comes out the other side of the hose? Well, hopefully you found out and you figured out that the water came out a lot faster. You could make it go a lot farther, okay, and it came out a lot faster than it did before, okay. Same idea happens backwards. If something's coming through a skinny tube and then gets into a wider tube, it's going to come out slower, okay. And this idea is because the amount of mass of your water that goes into whatever pipe you're looking at, your tube, has to be equal before and at the end of the pipe, okay? And that's really why the velocity speeds up and slows down, is because we're assuming our fluid cannot be compressed, okay? So the density can't change. So the mass of the fluid that enters and exits the tube at two ends must be equal to one another. Now, because that mass has to remain the same, the fluid either needs to go faster or slower depending on what happens to the diameter of the pipe. Okay, so if it goes from a fat portion to a skinny portion, your mass has to remain the same. So as it goes from a big portion to a small big diameter to a small diameter, the fluid must be getting faster. And then as it goes from a skinny portion to a fat portion, the fluid must be getting slower. Okay, so we get this idea of this, what's called the continuity equation. Remember, and the one thing people screw up with this is what is continuous. The continuity portion of this is the mass, okay? Continuity, we're talking about the mass has to be continuous, okay? So the mass flow rate has to remain constant, okay? The mass flow rate, so the amount of kilograms passing through a space in a given time, okay? So smaller pipes have less area, so they must have a higher speed, okay? And then the more massive pipes or bigger pipes have more area, so they don't need quite as high a speed. So the A1 is the area times area region 1 times the speed in region 1 has to be equal to the area of region 2 times the velocity in region 2. Okay. All right. Now, one thing you might not have noticed, okay, is that if you take a stream of water and you pour it, okay, as it goes down, okay, its speed increases, right? Gravity is acting on all those water molecules, making it's got some acceleration moving in the same direction as its velocity, and so the velocity of that water increases. Now, because that's occurring, the area decreases. And if you pour water over a long distance and you really look at it, you'll actually see that the area of your water actually goes down as it falls because it's speeding up. All right, kind of bizarre. Okay, so here's a good practice problem for us, and this will help us also practice units as well. It says water falling from a faucet has a cross-sectional area of 1.25 centimeters squared near the top when the speed is 0.5 meters per second. After it has fallen to a point near the bottom of the sink, the speed is 2.50 meters per second. What is the cross-sectional area of the stream at that point? Okay. Now, we know A1 V1 equals A2 V2. Okay, this is super easy, and we want to know the cross-sectional area of the stream at that point. So that's A2. So that means A2 is going to be equal to A1 V1 over V2. All right. Now you might be tempted, well, I've got A1, right? This is obviously A1. Okay, this is obviously V1, and this is obviously V2, and you might be tempted to throw those guys in there, but I want you to pause and just make sure you double check all your units. Notice that our area 1 is in centimeters squared, okay, and that our velocities are in meters. So this is in centimeters and these are in meters, so that means we got to change these guys. Okay, so V1 is in meters per second, so we're just going to do one of these real quick, and then we're going to do one of these the long way. Okay, so we want to convert it to centimeters per second, so we'll make our dimensional analysis. We'll put meters in the bottom, centimeters at the top. 1 is bigger than centimeters, and there are 10 squared centimeters in each one of those, so this becomes 50 centimeters per second. We won't worry about sig figs because we'll just worry about those at the end. And then so V2 would be exactly the same thing, essentially just multiply by 100. Okay, so this becomes 250 centimeters per second. All right, now we can plug these guys in. So our area 1 is in 1.25 centimeters squared. Okay, V1 is in 50 centimeters per second. Okay, and then V2 is a 250 centimeters per second. Now, because it's going faster, it should be a smaller area, so that should be what we get when we multiply this guys all out. 1.25 times 50 divided by 250, and we get 0.25, 0.25, and each of these have 3 sig figs, so it would be 0.250, and then centimeters squared because it's area, right, is what's left over. Pretty easy, okay? Bernoulli's principle, super fascinating. Okay, we're just going to barely scratch the surface of Bernoulli's principle, but first let's talk about what is going on here. Okay, so it says water accelerates as it moves into the narrower pipe because area is reduced. Okay, we've kind of already established this, right? We know that it goes because of the continuity equation, the idea that the mass has to be continuous. Your fluid has to be getting faster, right? It has to go faster when it goes from a bigger portion to a smaller portion, and this makes sense, right? Here's our leaf traveling through this pipe, and this leaf has some velocity. Here's our velocity vector, and it's pretty short. And then at the end, in the skinnier pipe, the velocity vector is bigger, and we understand that, right? We've established that in the last couple of slides that our velocity has to go up. Now, any times we have a change in velocity, that means we have to have had an acceleration, right? So that means we have to have had an acceleration on this leaf. That just makes sense, right? If the velocity of the leaf gets bigger, so it had to have had an acceleration acting in that same direction. So that's our acceleration here. That's that purple vector arrow. Now, what causes accelerations? Well, accelerations are caused by forces. Okay? Remember, F equals ma. All right, so that leaf got faster because an acceleration was happening to it, and it had an acceleration because there's some outside force acting on it. Some new net force is pushing it to the right. So that implies that the force in the bigger area here has to be bigger than the force in the smaller area. Okay, the force in area 1 has to be bigger than the force in area 2 in this picture. Okay, well, we also know that forces, right, that pressure is equal to force over area. Okay, so that implies that because this force is bigger, that the pressure in the bigger portion of our pipe has to be bigger than the pressure in the smaller portion of our pipe. Okay, so this is Bernoulli's principle in a nutshell. Okay, all right, and right here. Okay, the pressure in a fluid decreases as the fluid's velocity increases. This is Bernoulli's principle. Okay, the pressure in a fluid decreases as the fluid's velocity increases. All right. One of the big examples of this is airplane wings. Okay, airplane wings have this certain curved shape like this to make the air have to travel faster on top, because we know that the acceleration, okay, gives it because of continuity of mass. Okay, the air has to the mass of the air that goes from one part of our wing to the next part of the wing has to be equal to one another. But because of this curve, it makes it go a longer distance, so therefore it has to be going faster. And because of Bernoulli's principle, the fluid's velocity increases, okay, then the pressure decreases. So because the pressure because the velocity is higher up here, okay, higher up here, that means the pressure has gone down. Now, because the pressure has gone down, that means there's less force pushing down on it and more force pushing up on it. Okay, and so we have a net force that's giving us lift. All right, and so this gives us the idea of Bernoulli's principle. Okay, and then it also talks about how use the principle to explain the effect of a stationary car when trucks pass at high speeds. Okay, same idea here. When that truck passes, okay, that truck, the velocity of the air next to the truck is moving very quickly. Okay, and so that force of the quick moving air, that pressure provided by the quick moving air is very different, okay, than the pressure applied by the non-moving car. So the non-moving car actually gets sucked towards the truck. All right, so when you're next time you're on the highway, okay, you can kind of feel this going on. If you get passed by a semi, you can kind of feel your car get pulled slightly towards that truck. All right, or like another more kind of scary example is if you've ever been riding your bike on a very busy road and cars are passing you at like 40-45 miles an hour. Every time a car passes you, you can definitely feel your bike kind of turn towards that car, and that's Bernoulli's principle trying to get you killed. I'm just teasing. But anyway, so good luck with cars and trucks on the road and all that stuff. Do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.